Alright, so what we're going to do in this video is prove that addition on Fn is associative. So, uh, in other words, what we're going to do is show that for every A, B, C in Fn, the sum A plus B when added to C is equal to A added to the sum of B and C. So, before we start with this problem, let's recap what Fn is. So, Fn is defined to be the set of all lists of length n where each of the elements is a member of the field F. So it's the set of all x1 up till xn. Let's make that a bit shorter. So x1 all the way up till xn, where each xi is in F, where I ranges from 1 to n. So the definition itself might feel a bit wordy and abstract, but what we're essentially saying is the Fn is the set of all lists of length n, where each of the elements in the list is itself a member of F. So to make this a bit more concrete, let's say our field was R. And so members of R3 would look like this. Members of R3 would look like this. So we would have 3, 2, 7. And that would be in R3. Similarly, pi, e squared, -1 would all be in R3. And if we wanted to consider C3, the set of all lists of length 3 of complex numbers, where each of the elements in the list is a complex number, we would have something like 3 plus I, 2 minus 2I, and then, -1, where -1 is really -1 plus 0I, but we're going to just write it as -1. That's fine too. So, yeah. So this might seem like more concrete to you. You might recognize this as elements of the three-dimensional vector space. Although we haven't this you don't necessarily need the idea of a vector space to talk about the idea of a list, but you might recognize these as three-dimensional coordinates. In other words, like coordinates in the XYZ. Like this is a point here, XYZ. So that is an element of R3. R3 is the set of all lists, of all such lists of length 3, where each of the coordinates, in other words, is a real number. So F3 in that case would be the set of all lists of length 3, where each of the coordinates is a scalar, or rather, I should not say a scalar. That might make it a bit more, that might make it sound a bit ambiguous. I should say set of all lists of length 3, where each of x1, x2, and x3 are not real numbers, but in general members of a field, or the field that is under consideration. So that is what Fn is. How do we define addition on Fn? So we say if x and y are two elements in Fn, then clearly, first of all, we can establish that there have to exist n sets of scalars x1 through xn, and further another n set of scalars y1 through yn. All of these are scalars in F, obviously, such that x is described by these n scalars x1 through xn, and y is described by these n scalars y1 through yn. Cool. Now that we have that, we define x plus y to be equal to x1 plus y1 through xn plus yn. In other words, the list x plus y, each of these coordinates are given by the sum of the corresponding coordinates from these two lists. So what you do is take each coordinate at like the same place, or like at corresponding places, add them up, and that becomes the corresponding coordinate of the sum. So hopefully that makes sense. As a concrete example, consider you have the list 2, 1, 3 in R3, and you have pi, e, and 0 in R3 again. And when you add them, you will get essentially the list 2 plus pi, e plus 1, and 3. So hopefully that makes sense. Let me erase all this. Let me get rid of all this. Now we can start with our formal proof. So our proof is going to be like this. Suppose A, B, and C are elements of Fn. Then clearly there exist three sets of n scalars. So they're going to be a1 through an. There's going to be b1 through bn, and there's going to be c1 through cn, where all of these are in F, obviously, such that A is described entirely by these n scalars A1 through An, B is described by B1 through Bn, and C is described by C1 through Cn. So now we're going to consider the list A plus B added to C is going to be, what we can first do is just simply add, sorry, not simply add, I mean, what we can do simply here is just replace A, B, and C with their values, or what their representations. So A and B, A would be A1 through An, the list A1 through An, plus the list B1 through Bn, and all of this added to the list C1 through Cn. Now notice we can use the definition of addition on lists to get the list A1 plus B1, and that through An plus Bn, and we don't need these outer parentheses anymore in this expression, because we've now added two lists and converted them into one, so there's no ambiguity of addition anymore. So yeah, this becomes Cn. Now we can add these two lists, and now we maintain that since that every term of this list is A1 plus B1, we're going to preserve that as it is, so that it's that addition is represented as being performed first, because this is a quantity. A1 plus B1 is a quantity which is being added to C1. Similarly, every AK plus BK is a quantity which is going to be added to CK, and finally we get, and for K ranges from 1 to n, so finally we go to n. We say this is equal to An plus Bn, the quantity An plus Bn added to added to Cn essentially. Now you notice that A1, B1, Cn, An, Bn, Cn, and every AK, BK, BK, and CK are also scalars. So essentially they are all elements of the same field F. And we know that the associative property holds true. It's one of the defining axioms of a field. So clearly this sum will be associative. So we can write this as AK plus BK plus CK. And so let's replace that in this sum over here. Let me remove all of this. This becomes equal to list A1 plus B1 plus C1 up through An plus Bn plus Cn. Cool. Now we can break this list into a sum of two lists. We break this into A1 through An plus the list B1 plus C1 through Bn plus Cn. Again, we are going to break this list into a sum of two lists, and since this list is going to be represented as a sum of two lists, we want to put that in parentheses. So let me first write A1 through N first. Then we want to put this sum in parentheses, because we want to make sure, even though technically we know addition is associative, we are trying to prove it for um, like Fn. So we're not going to make any assumptions about uh, you know uh, order of addition right now, even though intuitively you might know that you can add them in any order, but this is what we're trying to prove. So b1 plus cn up till bn plus cn, this list right over here is represented as a sum of two lists, and so those will be put in parentheses to put priority on the order of addition, so that you can add these two lists to get b1 plus cn, which is then added to a1 plus an, a1 through an to get the list above. So this is going to be represented as a sum of two lists. We have b1 through bn and c1 through cn. Now you notice that we have everything we need, and all we need to do is replace a1 through n with a as we defined, b1 through bn with b as we defined, and c1 through cn with c as we defined. And so we get a plus b plus c, where a and b are added first and their sum is added to c, is equal to a added to the sum of b and c. So that is what we wanted to show, and that is what is desired. And so with that, we can say that we are done with the proof.